Welcome back. In the first lecture, we learned that probabilities are central to quantum mechanics. The outcomes of a quantum measurement, then discussed in the context of determining the polarization of a photon, these outcomes are randomly realized and they occur with certain probabilities. Today, still in the context of photon polarization, we will take a first look at the mathematical formalism by which we describe the quantum phenomena. So, we have the lamp, the photon source, and it emits light that is then probed by the polarizing beam splitter, such that photon that enters and is vertically polarized goes out in this upper output port. Photon that enters is horizontally polarized goes out at the lower output port. And photons which are not vertically polarized or horizontally polarized but have some other polarization properties, they will end up in one of the output ports with certain probabilities. Now, what we have here is an example of a so-called qubit, a quantum binary alternative. So it's a binary alternative because it's either vertical or horizontal, two outcomes only. And it's a quantum binary alternative because it refers to quantum properties of light. It doesn't refer to a coin where we have heads or tails as the alternative. So this is an example of what one calls a qubit, and in particular, it's the polarization qubit of a photon. There are other qubits that are used for quantum information processing, like the spin of an electron or internal states of an atom, and yet other physical degrees of freedom that can be used to realize qubits in the laboratory. But we will use this polarization qubit of the photon as the vehicle of discussion right now. So how are we going to describe the photon, the qubit that is emitted by the source and has certain polarization properties, but isn't necessarily just vertically polarized or horizontally polarized? But we begin by agreeing that the vertically polarized photon will be described by a two-component column which has 1 and 0, and the horizontally polarized photon will be described by the column which has 0 and 1. So we need a two-component object to describe this because we are talking about a binary alternative. So now the more general case, the arbitrary polarization, that would be described by a more general column which has two complex amplitudes, one for horizontal polarization and one for vertical polarization. And so that's what we will have in the general case for the description of the polarization of the photon emitted by the source. And so since this is in some sense partially vertically polarized and partially horizontally polarized, there's a certain probability for a photon of this kind ending up in the upper output port and a certain probability for this photon to ending up in the lower output port. And these probabilities are proportional to the absolute value of these complex amplitudes alpha squared and beta squared. And since we want these probabilities to be normalized to unit sum, because one of the two is always the case, we agree on using normalized columns for the description of these photons. So by convention, alpha squared plus beta squared is equal to 1. That's not absolutely necessary, but it's just convenient. Now, I was just stating as a fact that if we have vertically polarization described like this, horizontally polarization described like this, so this is, if I indicate an arrow, would be a photon that's polarized like that. This would be a photon polarized like that. And now we know from classical optics that superpositions of vertically polarized light and horizontally polarized light gives us all other polarizations, and such a superposition is just a linear combination of columns of this kind, which is exactly the kind of column that I have written down here. So this is a natural way of going about it. All right, so we describe photon of arbitrary polarization by this two-component column with an amplitude alpha for the vertically polarized contribution and an amplitude beta for the horizontally polarized contribution. If we do nothing else and just sorting them by polarizing beam splitter, there's a probability of alpha squared for getting the photons in the upper output port for vertical polarization, beta squared for the other output for horizontal polarization. Now, what else can we do? Well, we can have this arbitrarily polarized photon entering the polarizing beam splitter, and then the vertically polarized photons are selected, and those with horizontal polarization, that output port is blocked. So we have this column for the description of the incoming photons, and the outgoing photons have the beta component erased, and only the alpha amplitude for the vertical polarization is surviving the process. So what is happening here is a V selection, and the mathematical symbol for that will be the matrix that has zeros everywhere except a 1 in the upper right corner. Why is that the correct matrix? Because if we take this 2 by 2 matrix and process the alpha beta column for the incoming photon with it, we get the alpha 0 column as the result of this operation, and that's the correct description for the outgoing photon. So that's for V selection. Likewise, we can have H selection, where we throw away the vertically polarized photons and we keep the horizontally polarized photons. We have the 2 by 2 matrix which has zeros everywhere except a 1 in the bottom right corner. And just to see that this does the right thing, we apply this matrix to an incoming photon with arbitrary polarization, and we get just the beta amplitude surviving for the outgoing photon. So these matrices describe process where we select the vertical polarization or we select horizontal polarization. And as we can immediately observe, if we have one of the selection followed by the other selection, so we first have V selection, say, followed by H selection, then the overall effect is just a matrix that has zeros everywhere, and you apply that to the alpha beta column, then you just get nothing at all in the output port, right? So V selection followed by H selection gives us the null operation, so that the overall effect describes a beam stop. Nothing goes out. And if we do it in the reverse order, we do the H selection first and the V selection later, we also get the beam stop. All right, so we raised the board, and just as a reminder, we have this two-component column with amplitudes for vertical and horizontal polarization. We have this 2 by 2 matrix that describes a V selection. We have this 2 by 2 matrix that describes the H selection. And if we compose a V selection with an H selection in either order, we get the overall matrix of the beam stop. That just leaves us with nothing. Now, what else can we do? Well, if you have vertically polarized light and horizontally polarized light, you can convert one into the other by passing the light through a wave plate, a so-called half-wave plate set at the correct angle. So what would be the symbol for that? So which symbol describes the transition from alpha beta, and now we flip the polarizations into the beta alpha column? Well, that would be done by the matrix that describes this flipping, the flipper, and the simplest version of that has 0, 1, 1, 0, and as we can see, if we apply this matrix to the alpha beta column for the incoming photon, then we get the outcoming photon, which is beta alpha. So it indeed converts the amplitude alpha for vertical polarization into an amplitude for horizontal polarization, and the beta amplitude incoming for horizontal polarization becomes the amplitude for vertical polarization after passing the light through this flipper. Now we can combine the flipping operation with the V selection and the H selection, and let's just look at one such case. Let's do a flip first and then a V selection. And the 2 by 2 matrix that describes the overall operation is this matrix 0, 1, 0, 0. So this is flipping, and then V selection, and then this is the overall effect. Now, if we do the V selection first, and then we flip, we have a 2 by 2 matrix as the outcome, and that 2 by 2 matrix is 1, 0, 0, 0. And that matrix is different from this one, right? So here we V-select first, and then we flip, and then we have a different outcome. If we look at the effect on an alpha-beta column, here we begin with alpha-beta, and as we flip, we interchange beta-alpha, and then we V-select, so at the end we have beta-0. Here, in the second one, we begin with the alpha-beta column, we V-select, so we have alpha-0, then we flip, and we end up with 0 alpha. So clearly, the overall effect of flipping first, then V-selecting first, flipping second, the overall effect on the incoming photon is quite different. Which is just to say that for these operations, the order matters. It's not irrelevant in which order we do things. If we flip first and then V-select, that's one process. V-select first, flip later is a second process. Let me also note that if you flip and then V-select, and you would flip again, you would go from alpha beta to 0 beta. That's exactly what the H selection does. Well, let's see how the mathematics confirms this. We flip first, then we V-select, then we flip again. Now we have already seen that this product is the matrix 0, 1, 0, 0. And then multiplied with this matrix, it's the matrix 0, 0, 0, 1. So yes, indeed, we flip, we V-select, we flip again. The overall effect is an H selection. So in the second lecture, we have seen that polarization qubits, or qubits more generally, are described by two components, columns. One component for the vertical polarization, the other component for the horizontal polarization. And the optical elements that we use to manipulate the polarization qubit, such as a half-wave plate that interchanges vertical with horizontal polarization, or a polarizing beam splitter with one output port blocked that selects one of the two polarizations, these optical elements are described by 2x2 matrices. Optical elements in a sequence, well, that's described by a sequence of 2x2 matrices, which are then just multiplied with each other. And that's quite fitting, because as we have seen in the example of having a flipper followed by a V-selection, or a V-selection followed by a flipper, the order in which these manipulations are carried out on the polarized photon matters, just like the order matters when we multiply matrices. What we have seen so far, rather simple matrices describing relatively simple operations on the polarization qubit, illustrates the formalism in a simple context. The formalism itself is much more complicated and richer, and we will learn more about it in the following lectures.